You've eaten honey on toast, maybe stirred it into tea, maybe just admired a honeycomb in a nature documentary without really looking at it. 6 sides. Perfectly identical. Repeated thousands of times across a single hive, built by creatures with a brain smaller than a grain of rice. And you've never stopped to ask the obvious question: how does an insect that can't count, can't measure, and can't read a blueprint end up building the single most efficient shape in mathematics, over and over, without a single mistake? Mathematicians call it the honeycomb conjecture, the proven fact that if you want to divide a flat surface into equal-sized cells using the least possible material, the hexagon beats every other shape. Not the square, not the triangle, not the circle. The hexagon wins every time. Bees didn't read the proof. They just happened to build the winning answer, and that gap between what they know and what they build is the engine of this entire video. Stick with me, because by the end of this, you'll never look at a jar of honey, a bathroom tile, or even your own bones the same way again. Because the hexagon isn't just a bee thing. It's hiding everywhere, and once you see why, you can't unsee it. Here's the question the video is actually built around. Why does a shape matter enough that an entire ecosystem, arguably an entire planet, depends on bees getting it right? On the surface, a honeycomb looks like decoration. Wax walls, some honey, some larvae, tucked inside. But the hexagon isn't decorative. It's a survival algorithm, solved through blind evolutionary trial and error over roughly 20 million years. And it's the structural reason bees can do the one job nothing else on Earth does at their scale: pollinate a third of everything you eat. Start small. Imagine you're a single bee, and your only job is storage. You need to pack as much honey and as many larvae as possible into a wax structure using the least wax possible. Because wax is expensive, a bee has to eat about 8 ounces of honey to produce 1 ounce of wax. So the question becomes geometry. What shape, repeated over and over, covers a flat area with 0 wasted space and 0 wasted wall? Circles waste space. Gaps form between them, like coins on a table. Squares and triangles tile perfectly with no gaps, but their corners create weak points, and their walls, cell for cell, use more material than they need to. The hexagon is the only shape that tiles perfectly and uses the least total wall length to enclose the most area. It's the shape that lets a bee build a house using minimum material for maximum room. That's layer 1, an efficiency problem solved by geometry. Now scale it up. It's not one cell. It's a comb with thousands of cells, stacked back-to-back shared walls, an entire colony's food and future packed into a structure that has to survive heat, weight, and the constant foot traffic of tens of thousands of bees. Every wall a cell shares with its neighbor is a wall the colony didn't have to build twice. Multiply that saving across a comb with, in a strong hive, upward of 100,000 cells, and the wax savings compound into something enormous. The difference between a colony that survives winter on stored honey and one that starves. And it's not static. Bees build the comb slightly warm and pliable, then let surface tension and gentle heat pull the walls into a near-perfect hexagonal grid. Something closer to soap bubbles finding equilibrium than to careful architecture. The individual bee isn't drafting hexagons. The system is settling into them, the same way bubbles in a foam settle into hexagonal patterns purely from physical pressure. That's layer 2. The shape isn't just chosen. It emerges from thousands of workers and physics pushing toward the same efficient answer. Push it further. Some bee species build combs that hang in open air, fully exposed, no external hive shell to protect them. Giant honeybees in South and Southeast Asia build single sheets of comb, sometimes over a meter across, hanging from cliff faces or tree branches, holding tens of kilograms of honey, larvae, and bees against wind, rain, and gravity, with nothing but wax hexagons as the load-bearing structure. At that scale, an inefficient shape doesn't just waste resources, it collapses. The hexagon isn't a nice-to-have anymore. It's the only geometry that lets a comb of that size and weight hold itself together at all. That's the edge case. Take the same shape, remove every safety margin, and it's still the thing standing between the colony and total structural failure. So here's where your brain wants to land. The hexagon is impressive. Bees are impressive. End of story. A fun fact about nature's engineering. That's the intuitive takeaway. Except that framing misses the actual stakes entirely. The honeycomb isn't the important part. It's just the shape that makes something else possible. And that something else is the real reason this matters to you, personally, whether or not you've ever seen a beehive in your life. The efficient comb is what allows a colony to store enough surplus food to survive on a fraction of its members, while the rest spend every daylight hour doing something that has nothing to do with honey, moving pollen from flower to flower. That efficient, wax-cheap architecture is the only reason a colony can afford to send tens of thousands of workers out foraging instead of keeping them home. Producing wax. Take away the hexagon's efficiency, force bees into a wasteful shape, and colonies would need dramatically more resources just to survive, leaving far fewer bees available to pollinate anything at all. The shape isn't the achievement. The shape is the subsidy that pays for global pollination. The scale of what that subsidy buys is almost absurd once you see the numbers. Roughly 75% of the world's leading food crops depend at least partly on animal pollination, and honeybees are the single largest contributor to that work. A 2016 assessment led by the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services put the value of pollinator-dependent global crop output in the hundreds of billions of dollars annually. In the United States alone, commercial beekeepers truck an estimated 2 million plus hive colonies into California every February for a single event, pollinating the state's almond orchards, a crop that produces roughly 80% of the world's almonds and cannot produce a commercial yield without bees. And when the system breaks, the numbers move fast in the other direction. Since 2006, US beekeepers have reported average annual colony losses regularly exceeding 30%, some years spiking past 40%, tied to a mix of pesticide exposure, habitat loss, and colony collapse disorder. That's not a rounding error. That's a third or more of a country's pollination workforce disappearing annually and needing to be rebuilt from what survives. Here's the whole chain, laid out in order. 1. Geometry. The hexagon minimizes wax used per unit of storage, proven mathematically as the optimal tiling shape. 2. Physics and collective behavior. Thousands of bees and simple heat-driven material properties converge on that shape without any individual bee designing it. 3. Economics of the colony. Efficient storage means fewer bees needed for construction and maintenance, freeing the majority for foraging. 4. Ecological output. That foraging is pollination, at a scale of roughly a third of global food crops depending on it. 5. Human dependence. Entire agricultural industries, from almonds to apples to coffee, are built on the assumption that this system keeps functioning. Every level depends on the one below it. Pull out the bottom card, the hexagon, and the entire stack doesn't wobble. It collapses. So go back to that honeycomb you glanced at without really looking. 6 identical sides, repeated without error, built by an animal with no concept of geometry, no blueprint, no idea it's solving a problem mathematicians would later spend centuries proving optimal. It isn't decoration. It's not even really about honey. It's the quiet, load-bearing foundation underneath a huge portion of what ends up on your plate. Proof that some of the most consequential systems on the planet aren't held together by anything dramatic. They're held together by a shape, repeated patiently, until it becomes strong enough to feed the world. If a shape you've never thought twice about turns out to be propping up a third of your dinner table, imagine what else you've been walking past without really seeing. That's kind of the whole point of this channel. So if you want more of that, hit subscribe and I'll see you in the next one.